Okay, so this is our second week, and in the last week we talked about symbolic music representation. So this week we will following this trend of music media technology and talking about sound waves. So first of all, before we talk about the physics of sound waves and the basic acoustics, I will talk about the phonograph and viol. I remember we first addressed the music notations, right? So until the invention of phonograph, notation was the only way to record music other than through memory. So we talked about rote singing, right? Before the notation, musical notation was invented, and then when the sheet music came out, the music industry is basically the printing industry, right? The only way to record music, to spread music, is through the sheet, through the printed musical scores and notes. So until 1877, so yeah, about 1877, the only way to record music is through music notations. So this situation lasted actually for nearly 1,000 years, right? Thomas Edison invented phonograph, a device that records sound vibration waveforms by physical cutting in 1877. Viol records, which was firstly released in 1948, works in the same principle as phonograph, only with a cylinder replaced by a flat disc. So I'll show you some videos illustrating how phonograph works and how viol works. So basically the working principle is the same, but the phonograph takes the shape of a cylinder, but viol takes the shape of flat disc. Okay, so it's the viol records. It's a flat disc, but the working principle is the same. It's all by cutting the waveforms on a physical affordance, right? It's by physical cutting. Okay, so here is our first introductory video. Let me play this.
From an era of going to opera and musical concerts, to listen to music, to an era of listening music in our home, the invention of gramophones would be the first step for our modern entertainment. It is also the most important invention that changed the music industry overnight and spread music to everyone around the world. In this video, we're gonna explain how these gramophones can produce music without even electricity. If we take a look at a gramophone, it produces sound when we place a stylus needle on a rotating record disc. The record disc contains music data and the gramophone converts these data into sound. Before we talk about how a gramophone produces sound, let's learn a few things about how sounds are recorded into a record disc. In other words, vinyl record. What we call sound results from the vibration of objects hitting our eardrums and making them vibrate. In other words, the vibrations we can hear are called sound. Imagine a pen going up and down with the sound waves. If we put a paper underneath, it will draw a line repeatedly. In order to record the sequential motion throughout the time, let's pull the paper strip with some constant speed and you will see the sound waves recording with time. It is the same idea in recording the vinyl disc. The vibrations from microphone are sent to the cutting lathe and move the diamond cutter side to side. The diamond cutter etches these vibration onto a rotating lacquer disc. Lacquer disc is just an extra smooth aluminum disc coated with lacquer on top. By moving the cutter head on the rotating disc, the cutting paths will not cross each other and forming a spiral path leading towards the center. The lacquer disc after the recording process is called the master disc. But to mass produce these records, there are still many processes left. First, a master disc is sprayed with silver chloride and coated with silver to conduct electricity. After that, it is immersed into a liquid tank of dissolved nickel. When immersed, the nickel is fused to the silver surface by electrical charge. This process is called electroplating. When the nickel surface is removed from the original lacquer disc, we get the negative image of the grooves on the nickel disc. Negative image is just an opposite pattern of the grooves on the master disc. By using this nickel negative disc to stamp the grooves onto a heated vinyl, we get the vinyl record which has the same groove pattern as the original lacquer disc. One nickel disc or stamper can be used for about 1,500 times before losing its quality. This is just an overly summarized process of record making. In reality, the processes are more complicated and each factory has its own production techniques. Since we now understand how sounds are recorded onto a disc, let's move on to how gramophones can produce back the sounds recorded in a vinyl record. We can separate the gramophone into three main sections. The spindle that the record sits on and rotates on, the stylus that moves on the record disc, and the horn assembly that amplifies the sound. These gramophones don't even need electricity, and here is why. The record is rotated by the spindle. The spindle is driven by the spring motor inside the gramophone. The spring motor is powered by one or two torsional springs. The outer end of the spring is fixed at the motor housing and the center end is fitted at the gear shaft. The gear shaft is driven by the worm gear, which has a mounting hole at the end. If you wind up the spring and release it, it will quickly goes back to its original position. In order to produce the rotation via the housing and not from the wind-up gear, we need to make the worm gear one way only for winding up. For that, a spring called non-return spring of the same size as worm gear is inserted on the shaft and the end is fitted at the motor frame. When we rotate the worm gear to wind up the spring, the non-return spring is in expending state, making it easy to rotate. But when the spring went to rotate back the shaft, non-return spring is in contracting state and so it tightens on the worm gear, making it unable to rotate. By limiting the rotation on the worm gear makes the spring recoils on the spring housing. Even though the spring recoils with enough power, the duration is so short and the speed is so high for the vinyl record that needs longer duration with steady speed. To be able to rotate the record for many turns, the spring main gears is connected to a much smaller gear. If the two gears have the same size, the driven gear will rotate the same revolution as the driver gear. But if the driver gear is 6 times larger than the driven gear will rotate 6 times for every revolution of the driver gear. Same principle is used in our spring motor. When the spring main gear is used to drive the much smaller gear which also drives smaller gear, we can get so many revolutions from a few turns of the spring winding. In the winding part, since the spring shaft gear is about 3 times larger than the worm gear, we must rotate 3 times in order to wind up the spring 1 turn. With that low gear ratio and the leverage on the hand crank make it possible for anyone to be able to wind up the gramophone easily. Even though we can get so many revolutions out of few turns from the spring, the rotation speed is still so high at the smaller gears. A normal vinyl record can play the songs at 70 revolutions per minute, or 130 revolutions per minute, depending on the recording rate. To control the output speed of the gears, we add a governor speed control. It is just a shaft with hanging weights, and it is connected to the spindle by a worm gear set, which will limit the spindle rotation speed. When the speed is getting high, the weights on the shaft move outwards, due to centrifugal force. The weights also pull the flange to one side. The flange is controlled by a small felt pad, connected to the speed control dial on top. When the speed is high, the weights move outwards and pull the flange towards the felt pad. The friction between flange and felt pad slows down the rotation speed. When the rotation gets slower, the weights move inward and push the flange back, reducing the friction between the flange and the felt pad. Reducing the friction increases back the speed, which will expend the weights and pull the flange towards the felt pad. Since it is happening in a feedback loop, we can get the decent speed at the spindle. For producing sounds, when we place a stylus needle on the rotating record, the grooves on the disc move the needle back and forth, producing the same vibration that were used for cutting these grooves. But these vibrations are not big enough to produce any audible sound. For that, the motion of the needle is amplified by the longer lever, which is attached to the diaphragm. Therefore, the small vibrations of the stylus needle can produce the larger vibrations on the diaphragm, hence, producing the audible sound. This is further amplified by the horn assembly to make it loud enough for home entertainment. When the sound waves travel through the horn, the increasing area of the horn makes the sound waves resonate, and hence getting louder at the end. Depending on the type of gramophones, 1 or 2 records can be played with single winding. After that, you need to rewind the spring to listen again. Hand crank gramophones become less popular when the electric motor ones were produced. At this point, we hope you understand how gramophone works and how the sounds were recorded and maintained. In this era of digital and electronics with all its glory, it is so inspiring to know how we humans had started, and how far we have come. To see more explainer videos like this, please like and subscribe to our YouTube channel.
Okay, so this animation, this video illustrates how a gramophone. So this is a really old-fashioned like vinyl record player, because later on when the electricity came out, everyone plays, even if they still use this physical cutting of the vinyl, but they play the vinyl through the speaker. So we'll talk about this in a minute. The speaker actually uses this electromagnetic induction. So this is utilized, the field of electricity and magnetism. But this video actually shows you when before the electricity was invented, right? How people play the music through a gramophone. So by purely engineering using the spring and this spinning and the speaker, there's no electricity, so everything is old-fashioned, but there's still music playing. So I think this is quite inspiring for us, because we live in this digital era. Probably we cannot imagine like what was like right before electricity was invented. So in this next video, it talks about the vinyl, but here it basically talks about the working principle of vinyl as an analog signal versus the digital signal. Okay, so analog means the signal is continuous, but digital means it is sampled or is discretized. So and here, when this device play the vinyl, it uses electricity to drive the speaker to make sound. Okay, so this is more a more advanced device to play the vinyl records. So let's watch this.
This episode of Real Engineering is brought to you by Skillshare, home to over 20,000 classes that could teach you a new life skill. The humble disc record is not often properly recognized for the impact its development had on the modern world. On the face of it, these records are just consumer products that allow music to be sold to the masses, a concept that itself only reached the mass market about 100 years ago. The truth is, the impact of this technology goes way beyond consumption of pop music. In some way, the record's closest comparison is the printing press. The printing press is often considered to be one of the most important inventions in history due to its ability to quickly and accurately reproduce ideas in written word, which in turn greatly accelerated the transfer and exchange of knowledge. The ability to press audio to record so that it can be reproduced in scale did the exact same thing for audio. It functioned as a vector for cultural exchange. And the revolution in recording technology, ushered in by electronic and audio engineers that developed the technology, is the foundation upon which modern communication systems stand upon. Of course, these days, most of the music we consume is digital. The internet has changed not only the way we consume music, but also the amount of music and the music itself. Curiously, while this is happening, vinyl is seeing a year-on-year increase in sales. Even more curious is the fact that half of the people who buy an album on vinyl stream it first. It remains a point of contention whether analog formats, such as vinyl, are actually superior to their modern-day digital counterparts. Is vinyl's resurgence just consumers seeing yesteryear's technology through rose-tinted glasses, a yearning for a physical connection to their music, or does the music really sound better on vinyl? To understand the differences between these two, we first need to understand the commonalities. No matter which format is used, analog or digital, both require audio data to be created by a recording device. The simplest of these would be the microphone, which turns air pressure into either a digital or analog signal, which can be replayed as an electrical analog signal. This process was first put into use in 1877 by Thomas Edison. While working on the telephone, Edison decided that it would be worth investigating if sound could be recorded for later reproduction. Edison designed a rotatable cylinder disc wrapped in tinfoil, which was turned by a hand crank. Attached to the disc was a needle, which in turn attached to the mouthpiece, which adjusted the pressure of the needle on the disc. Edison talked into the mouthpiece while turning the hand crank at a constant rate, and as predicted, the pressure of the sound waves imprinted a proportional indentation, which was analogous to the sound his voice created. When he finished recording, he returned the needle to the start. The indentations which were caused by his voice could now be played back by rotating the cylinder.
Mary had a little
This invention, the phonograph, was the first example of playable recorded sound, and for all intents and purposes, the vinyl record is essentially an iteration of this technology. The first vinyl record was pressed in 1948 by Columbia. Specifically, it was this recording on 12-inch. Vinyl records work on the same principle as Edison's phonograph. A 3D representation of a sound wave is physically pressed onto a vinyl record. An impression is first created by a cutting head. The cutting head creates an impression that is a direct analog of the sound wave. This process creates a master that will go on to create a stamper that molds each record. When a record is played, the frequency of the wave that you will hear will depend on how stretched out the wave is on the media, and the volume will depend on the size or amplitude of the wave. This audio information will be pressed onto the vinyl in one of three fashions: via horizontal modulation, vertical modulation, or via a compromise modulation of 45 degrees. Horizontal modulation is always preferable over vertical modulation. And this is because the vertical modulation leads to more distortion and allows for less amplitude due to the inability for the stylus to track the groove, and also a propensity for the needle to bounce off the wave if the amplitude is too high. But if we run with only horizontal modulation, we can only play audio in mono, and we don't have stereo separation of sound. Accordingly, we use a compromise modulation of 45 degrees in order to allow separation of audio from mono to stereo.
Okay, so here it introduces different ways of cutting. Okay, so you can cut it horizontally, and you can cut it vertically. So when you cut it vertically, when you cut it too deep, the needle might be bounced up, right, off the track. So to combine these two methods, they use this cutting with certain angle, so combining horizontal and vertical modulation. You can see my screen, right? I'm sharing the screen, so you can watch the video, I think. Yes, so I'll play the video here and we can just watch this together. Okay, I think it gives a better illustration with the pictures and the animation. So I think it will be a good source for teaching. Yeah, so I'll continue with this recording.
Compromise modulation of 45 degrees in order to allow separation of audio from mono to stereo. As the stylus follows the groove, it moves a magnet wrapped in a small coil of copper wire. This causes an electric current that corresponds to the groove on the vinyl, which in turn corresponds to the physical sound waves that were originally recorded. The electric current can now cause a physical movement of the speakers, which will reproduce that sound pretty faithfully. Some vinyl enthusiasts argue that this smooth, continuous reproduction of sound from analog to analog is more faithful than digital music. Part of this argument stems from the difference in how digital music is reproduced. High-quality digital audio data is typically sampled 44,100 times per second. Close inspection of the wave function produced from binary code shows that rather than the audio data being smooth and constant like real life, the audio data is jagged and technically non-continuous. Because there is an infinite amount of data between each second of audio, we have to sample the audio in regular intervals to minimize the size of our digital file. Comparing this to the smooth, continuous waveform that is imprinted in vinyl, you would think this might cause some loss in information.
Okay, so this is the information that's provided. Might be some argument for your homework. Yeah, if you already see assignment 2. So this is certain arguments that some people brought up when they say why they feel digital signals or digital audio is inferior to analog signals. But this is actually not quite true. We will address this later on. I think this is also addressed in this video. Okay.
Is a loss of information or not depends on whether the 44,100 sample rate is high enough to be functionally the same. An answer to this was proposed in 1928 in a pivotal paper published by Swedish-American electronic engineer Harry Nyquist, and was subsequently proven by Claude Shannon in 1949. They simply found that to recreate a frequency, we only need to sample each individual wave at least twice. If not, the frequency will be digitized with a lower frequency. The maximum perceivable frequency a human ear can detect is 20,000 Hz, and so digital recordings with a sampling rate of 44,000 Hz can capture even the highest frequency possible. Thus, the sound produced by a speaker using digital audio is effectively the same sound as analog recordings. In this case, the argument that analog recordings are more faithful does not meet the scrutiny of science, and in theory, digital and analog music recordings should sound functionally the same if played on the same equipment. The argument does not end here though. There are some constraints to how sound can be recorded on vinyl. Interestingly, these constraints largely explain both vinyl enthusiasts' preference for the media and also why some might argue that digital recordings are a superior format for storing audio. The major constraint that impacts vinyl is simply its limit in data storage. This is simple to understand. A 12-inch record can only hold so much information in the format we've described. Each rotation of the record takes 1.8 seconds. The next question is how many times each 12-inch record can rotate. Two things affect this. The frequencies found in bass notes require the groove of the record to swing out wider, just as the speaker also thumps out wider when it plays bass. Waves of higher amplitude that produce louder sounds also require wider grooves. This means that both low-frequency sounds and loud sounds both eat up valuable vinyl real estate. This in turn means that if your record has bass or is loud, like most contemporary music, there's not going to be a whole lot of space on the record for your songs. The net impact of this is that there is a volume and time constraint on vinyl record that does not apply to digital music, which has huge ramifications for how we listen to music and how music is created and mastered. Vinyl's limitations do not end here. If the frequency is low and the amplitude too high, the stylus can become prone to bounding off the wave due to the path the stylus has to take up the wave at speed. This can cause the record to bounce around and skip if not accounted for. Accordingly, bass needs to be center panned in the mix, and a specific mix has to be applied to the music recorded to vinyl to stop this from happening. High frequency sounds also need to be taken into consideration while cutting a vinyl record. The issue is commonly referred to as the sibilance issue. Sibilance is an unpleasant hissing sound associated with S sounds and other high frequencies that anyone who's watched my older videos will be painfully aware of. High frequency waves cause two fundamental problems in vinyl. High frequency sounds mean the waves are very tight together. The stylus has to surf these waves and turn extremely tight corners. When the curvature of the groove becomes tighter than the tip of the radius of the stylus will begin to plow through the groove and you will end up with distortion. On top of this, extremely high frequency waves can lead to the cutting head that cuts the record to overheat. This is simply a matter of the cutting head having to take a longer path and having to do more work to cut these waves. The overheating can lead to inaccuracy in the cutting process and in turn to noise and distortion on the final record. To counteract the negative effects that extreme low-end and high-end frequencies have on vinyl, a group of American engineers developed what became known as the Recording Industry Association of America curve in the 40s and 50s. The RIAA is an equalization scheme that is applied to the sound before the master lacquer is cut. In essence, this curve reduces bass content and boosts treble in the record. Without this curve, low frequencies take up so much space that each 12-inch LP would only allow for 5 minutes of music. In addition, boosting the treble hugely lowers the surface noise that vinyl can produce due to the path the stylus takes. This is also why a turntable requires a special phono preamp. In addition to amplifying the tiny voltage created by the turntable's cartridge, the preamp applies the inverse of the RIAA curve, perfectly restoring the music's natural balance and minimizing the size constraints that are intrinsically linked to the nature of the media. So we've painted a complicated and grim picture for vinyl as a storage media. The actual truth here is that there is no functional difference in the audio quality between digital and analog formats. And studies show that the human ear and brain is not sufficiently equipped to distinguish the difference between sound produced from analog signals when compared to a digital counterpart. At the very least, this is enough to debunk the notion that digital music formats are a lesser quality format than analog formats. An important question to ask here is why are people that understand these concepts still drawn to vinyl? There's a number of simple answers to this question. Part of it is the nostalgia factor. People have positive personal associations with the vinyl format from their youth, and these associations invoke an emotional state that induces a sense of comfort. And although there are no discernible differences in theoretical audio quality, vinyl does have a specific sound that is imparted due to the mastering process. Mastering is the process by which the final song is mixed for the final device it will be stored on. Over the past 36 years, due to the removal of the physical limitations of vinyl media and the spread of digitized music, songs have become increasingly louder and increasingly more compressed. In essence, this means that the sound wave becomes compressed, forcing the quieter parts of the song to become relatively louder and the louder parts relatively quieter, the net effect being a louder, noisier song. As a result of this trend, a vast majority of commercial music releases have been subject to a somewhat arbitrary loudness war that has forced them to increase loudness to keep pace. It has also resulted in increased use of compression of the music, which some would argue has resulted in a loss of detail and nuance in the final sound. This development has been criticized by a number of prominent audio engineers and is part of the attraction towards vinyl. Some people prefer vinyl for this reason. Music properly mastered for the medium is to a certain degree immune to the effects of the music loudness wars, and in some cases, this can mean that the more nuanced parts of the songs are easier to pick out for a trained ear. Really though, given that this same information can be recorded on a digital format and replayed exactly the same way, the answer to this question is that digital and analog formats are functionally the same in the quality of sound produced, and any preference for one media or the other is really just that, a preference. The longevity and iconic status of the vinyl record as a music format cannot be ignored though. Despite the shortcomings we've described, it is an incredibly durable and elegantly simple medium. This is probably best exemplified in the golden plated record sent on Voyager 1 in September of 1977. It's hard to believe, but 12 million miles away from here, this record is floating through space. Its cover contains simple instructions for playback based on certain universal constants, and the record itself contains a high-resolution snapshot of 200,000 years of human culture. Unless the Voyager 1 suffers a direct impact or encounter heat that may melt the record, this record in theory should outsurvive even our species. Just as the technology for storing music has advanced, the technology for mixing and mastering music has too. It has never been easier to get into music production, thanks to programs like FL Studio and Ableton, which give you a virtual production room with all the tools you need to create a song of your own.
Okay. So I think this video gives us some very good explanation about why some people prefer vinyl and what's the difference between vinyl. So in terms of sound quality, or in theory, there is no difference, right, between the analog signal and the digitalized signal. But in terms of music production, right, because there are certain limitations on vinyl, and also the loudness war, right, mentioned in this digital music production. So there are certain ways, different paths people choose for music production, which causes the difference between the music made on vinyl and the music played through our phone or the computer speakers. So I hope this gives you some inspiration about how to do your homework. Also, reflect on the fact why some people prefer vinyl over digital, or some people also argue that because digital has more like capacity and it doesn't have many physical limitations as vinyl. So some people may have a preference over the digital format of music. Okay, so let's continue with this. So there's a lot of videos. I think our first hour will mostly going through these basic ideas, and I will gradually introduce the concept of sound waves. So the basic of music is the sound. So understanding the sound waves, especially the sound waves produced by instruments, right? Because sound waves can be produced by anything, vibrating and making sound waves, and noise, and the plane flying by, and anything can produce sound. But because this is a music technology course, so we will focus on the sound produced by musical instruments. But before that, let me introduce you how the speakers make sound here. So in this video, it will talk about the working principle of the speaker, and you can know, like, basically especially for the dynamic microphone, this is the working principle. Okay, it uses the electromagnetic induction, and this video will also introduce you some basic concepts of the sound waves. Okay, so let me play this.
I'm Jake O'Neill, creator of Animagraphs, and this.
Okay, answering the chat. those videos can be found in the playlist. Okay, so if you go to our course website, the modules, you open this page. Yeah, this is Sound Waves playlist. So all the videos that I will play or will not play in the class will be here. Okay, this is a good reference. I will play some of the videos here, but for these videos, I won't play in the class, but it's a good reference for you to familiarize yourself with the concept and understand more of the course. Where are the ones? Yes, I think I will play most of the first. Yes, the first 1, 2, 3, 4, right? And will be played in the class. Yeah. So all the videos played in the class will be in this list. Okay. Any questions? Okay, if not, I'll continue to. Oh, the first one on vinyl. Okay. Oh, the first one on vinyl is on another one. Yeah, you are right. Sorry for the confusion, because this is for the sound waves. The first one on vinyl will be. Okay, let me see. Because this is my channel, and this it will be in the module here. Okay, so yes, so all the music media kind of related videos will be in this playlist. Okay, so the vinyl is here. Yeah. These two are the videos I just played. Okay. Okay, sorry for the confusion. Yeah, I forgot about this. Okay, thank you for bringing this up. Okay, if there's no other question, let me continue to play this video and introduce you about how the speakers work.
I'm Jake O'Neill, creator of Animagraphs, and this is how speakers make sound. The basic speaker design has a motor that drives the speaker back and forth, attached to a cone to translate this movement into pressure waves that travel through the air. Let's look at each part in depth. The motor. A voice coil and magnet work together to form the speaker motor. The voice coil has a long section of thin copper wire wound many times around a heat-resistant cylinder called the former. When electricity flows through the copper windings, it naturally generates a surrounding magnetic field. This phenomenon is what makes an electromagnet. An electromagnet can act just like a permanent magnet, and yet, incredibly, its polarity, or positive and negative pole orientation, and magnetic intensity can be changed by altering the supplied electric current. It can instantly be made stronger or weaker, reversed, or turned off completely. A large permanent magnet or natural magnet surrounds the voice coil. This magnet has a top plate and a backing plate with a pull piece through the center to focus the magnet's field through the gap. An intricate electrical signal flows through the voice coil windings, causing it to move back and forth as its magnetic field pushes and pulls against that of the permanent magnet. This electrical current is a precise replica of the audio that was originally recorded. In fact, the entire sound is contained in this impossibly detailed signal. The cone and suspension. The cone translates voice coil movement into waves that travel through the air. It has its own flexible suspension system, made up of the surround on the outside and the corrugated spider at its center. The dust cap keeps debris and unwanted material out of sensitive internal areas. Underneath the dust cap, The voice coil's copper leads attach to more flexible wires called tinsel leads that can smoothly deform with intense speaker movement. Recreating the whole symphony. If a speaker only moves back and forth, how does it reproduce an entire symphony of sounds at the same time? Let's look at basic sound wave operation. Air is an elastic medium, meaning that it returns to its original shape once an acting force is removed. Speakers push and pull air molecules, making them ram into each other in a domino effect. This wave reaches and moves your eardrum, which sends a signal that your brain interprets as sound. You could even say that hearing is just movement detection. While it's often easier on paper to draw waves as a bouncy line, in reality, sound waves are three-dimensional areas of high and low pressure. When we turn up the volume, the speaker pushes harder, sending more forceful waves through the air. The sound wave's pushing force is its amplitude. To make high and low sounds, the speaker vibrates faster or slower. The wave rate is its frequency measured in hertz, or in musical terms, its note pitch. From waves to music.
Let me stop here and maybe let's review this. I think this is a good, real good animation to talking about the amplitude and frequency. Okay, via this animation of sound waves. Okay, let me see. Should be here. Okay, so you can see how the amplitude was described here.
Pressure. When we turn up the volume, the speaker pushes harder, sending more forceful waves through the air. The sound wave's pushing force is its amplitude.
You can see with the amplitude getting higher, actually, the compression here is getting, it's getting more tight, I would say. You can observe this part, okay, the change of this part when the amplitude is getting higher. And also you can hear, right, the sound is getting louder. Right, this is compression. The compression is getting tighter.
To make high and low sounds, the speaker vibrates faster or slower. The wave rate is its frequency measured in hertz, or in musical terms, its note pitch.
So this is a frequency or note pitch. So when the frequency is higher, the sound actually vibrates faster. Okay, so you can see here will be more of these patterns of compression. There will be more compressions here with higher frequencies, but with lower frequencies, the compression pattern will get more sparse.
From waves to music. A musical instrument produces a unique waveform when played. Just one note has low, mid, and high range vibrations combined into a complex sound wave. The most apparent frequency of a vibrating guitar string may be a G note. And yet many smaller twitches and movements travel through the string at the same time, producing tones that your ear also detects. Here's the exact same guitar string pluck sound, but I've isolated distinct frequencies from low to high.
Okay. So these are the fundamentals or the harmonics of you. When you pluck this string, it actually produces these standing waves. So this is what we will talk about in this lecture: the standing waves and the upper harmonics, the fundamental, second harmonic, and all those harmonics, when they combine together, they form this complex tune which is the musical pitch. Okay.
A single instrument note is really a sandwich of frequencies where one main frequency stands out. This frequency sandwich is known as an instrument's timbre, or unique sound. It's making a G note, yes, but it still definitely sounds like a guitar and not a piano. When two or more instruments are played together, the unique
Okay, so here it plays the J note, which is the same pitch, right? The same frequency here, presenting by the waveform is different, and also the timbre, right? The timbre is different. This is because the upper harmonics are different. The component of upper harmonics and also the amplitude of upper harmonics are different for those two instruments, the guitar and the piano. And we will also talk about the physical construction of guitar and piano and why they produce different sounds, right? Simply speaking, is that because here in the guitar, it's a plucked string, right? You pluck this string, and when you pluck this string at a certain position and you release that, it will vibrate and produce a sound wave like this. But for piano, actually, it is it's used as a struck string. So basically, there is a hammer. When you use the hammer to knock the string, and this produce the sound for piano. And because this excitation or the way you play or the way you make sounds are different for guitar and piano. That's why they make different timbres. Although these two notes or these two sound waves are of the same pitch, same frequency, but they have different, combinations of upper harmonics.
sound waves combine into one even more complex unified wave. Matching frequencies from each instrument merge, becoming louder but indecipherable from the other. However, many unique frequencies from each instrument's distinct timbre remain intact and undisturbed. With a little effort, our ears can still pick out these individual instruments from the mix. The human ear can discern sound vibrations between about 20 Hz and 20,000 Hz. That's a lot of available frequency to work with. High frequencies ride on the back of rumbling bass waves to reproduce an entire orchestra in one impossibly complex, unified waveform. It's entirely possible for one speaker to handle the whole sound, like earphones, for example. However, in large spaces where sound waves need to travel further, some audio setups divide specific frequency ranges between specially designed speakers. A speaker intended for low, slow frequencies has a much different design than speakers made for high and fast frequencies.
Okay, so it gives the introduction to how the speaker works and also some basic knowledge of sound waves and instruments. Any questions so far? So we will also talk about how so it talks about how the two sound waves, right? They add up together or they superposed upon each other. So we'll talk about how this process, how this process was like implemented. So there will be no interfere. So when you add these two waveforms together, they will simply add together. So will be no interfere between two sound waves. So if you think about this, if there is any interfere between those sound waves, they will be difficult to distinguish different instruments we're playing, because they can be simply add together and they can be separated after they were added up together. This is called a linear system. So this reduces much of our efforts for the digital or sound processing. Okay, so we'll get into those details later on. But here, because it's talked about the speaker, actually my microphone works in the similar, principle as the speaker, just reversely. So here, the mostly used microphones are dynamic microphone and condenser microphone. So actually they work in different principles. Okay, so in the previous video, it talks about the speaker work. This is the same principle as how the dynamic microphone works. Okay, it's also known as moving coil microphone. So it works via electromagnetic induction. Okay, they are robust, relatively inexpensive, and resistant to moisture. This, coupled with their potentially high gain before feedback, makes them ideal for onstage use. So all the microphone you see, the singers use on stage, where they hold the microphone and they walk around. This is a dynamic microphone. So these are the features of dynamic microphone. For the working principle, it's similar than the speaker. Okay, there is a magnetic, and there will be coils surround the magnet, and via the electromagnetic induction, it will produce the electrical signals. Sorry. So for condenser microphone, there is a little bit difference there in terms of working principle, although it also uses electricity. It's called a capacitor microphone or electrostatic microphone. So there will be a diaphragm. So diaphragm acts as one plate of a capacitor, and audio vibrations produce changes in the distance between the plates. So because the capacitance of the plates is inversely proportional to the distance between them, the vibrations produce changes in capacitance. These changes in capacitance are used to measure the audio signal. So this basically uses the okay. So maybe let me get to this first. Okay, this is an illustration of the working principle. This is for the inner working of dynamic microphone, right? It's the similar as the speaker. We just saw there's a magnet, permanent magnet, and there's electric coils around this. And when the sound waves came in, and it will so when the sound waves come in, it will move the magnet, right? And then through electromagnetic induction, there will be electricity produced in this coil, and then it will be transferred into an electric signal. But for a condenser microphone here, you can see this called membrane or diaphragm. Okay, so in this diaphragm, when the sound waves comes in, for high and low frequencies, it will give you different distance. Okay, here. So the distance on the diaphragm records the shape of the sound wave, and this different distance will induce the different types of different electricities, and this will be transferred. The distance here will be transferred into a digital signal okay, that encodes the information from the sound waves. So this is the so there's an electrical resistor. So these are the two different microphones that's most used by us. And the condenser microphone is more like used in the studio because this is more sensitive and it picks up more sound. Okay, more like sensitive, more subtle environmental sound. That's why it's used like in a quieter or more closed, room, and it produces higher sound qualities. So for dynamic microphone, yeah, so it's used on stage. So even though there's crowd, crowd of people and also like many background noises, it won't be too sensitive. Okay, for those sound. And here is a video introducing the difference between dynamic microphone and condenser microphone. Okay, I'm going to play this now.
So let's have a look at how dynamic and condenser microphones work. Dynamic microphones use electromagnetic induction to convert sound into electricity. Now that might sound complicated, but all it means is that the diaphragm of a microphone is attached to a coil of wire, and that coil is placed inside the magnetic field of a very strong magnet. As sound waves hit the diaphragm and the coil start moving rapidly inside this magnetic field. As a result, an electric current will start flowing in the circuit, and this is what we call electromagnetic induction. The pattern of movement that's caused by the sound waves will be translated exactly into the current that's output by the circuit, and therefore, you will get an electrical signal that closely resembles the incoming audio signal. This operation is basically the reverse of how a speaker works. Now, condenser microphones work slightly differently. Their diaphragm is a metal plate, which sits in front of another metal plate, called the backplate. These two plates together act as a capacitor, which is an electrical device that can store small amounts of electrical energy, a property surprisingly called capacitance. As sound waves hit the diaphragm, it moves back and forth, changing its distance from the backplate, which in turn changes the circuit's output signal. Like with dynamic microphones, the electrical signal that's produced will closely mimic the waveform of the incoming audio signal. Unlike dynamic mics, however, condenser microphones need external power because the diaphragm and the backplate need to be electrically charged to function. They are what is called active, as opposed to dynamic microphones, which are passive. That power can be supplied internally from batteries or externally via a power adapter or USB connection. But most commonly, it's supplied from the preamp the mic is connected to via an XLR cable. This is known as phantom power.
Okay, so this is a basic introduction to mostly used microphones. There are also other types of microphones used. But we are not going into the details of all those types of microphones. So next, after we talking about those devices, right? Speakers, microphones, viols, gramophone. Now we're going to talk about the physics of sound waves. So here is the first video that talks about what is sound. Okay.
Why does everything around us generate sound? Also, there are a whole variety of sounds. Running water, a cell phone, music, someone's voice.
Hello?
The list of sounds you hear throughout a given day is endless. But when you are shown what sound looks like, inevitably you are shown something like this, which sounds like this. And to me, that doesn't make much sense because you never hear that sound in the real world. In this branch episode, let's try to better understand what is sound. Let's start with a simple sound. That was popping an inflated polka dot balloon. This polka dot balloon is filled with high pressure air particles, and when popped, all these particles rush out and hit the adjacent air particles. Those particles hit the next set of adjacent air particles, and so on, thereby creating an expanding shell of air particles just bouncing into one another. This is called a pressure wave or sound wave. This wave travels throughout the room, and eventually the bouncing air particles apply a force to your eardrum, which causes parts of your internal ear to move. Then your brain processes this motion in your internal ear and tells your cognition that, oh, this motion in my ear sounds like a popping balloon. Let's rewind, go back, and take a deep dive into what this sound wave looks like. Even though popping the balloon makes a relatively simple sound, when we take a cross-section and zoom in, on a molecular level we can see the complex pattern depicting how the air particles are bouncing into one another. This pattern is produced within 1/10 of a second after the balloon is popped. You may ask, where does this pattern come from? Well, the high-pressure air particles rush out and generate a high-pressure wave. But when they do, they create a low pressure void in the balloon's center. The air particles rush back in to fill this void, thereby generating a low pressure wave. When the particles rush back in to fill this void, they rush in too much, thereby creating a second high pressure zone. This cycle repeats itself, and each time it does, it generates a high pressure and low pressure wave, which can be graphed. This graph shows the pressure waves, or waveform, produced by popping a balloon. The vertical axis is pressure, or the amount of force the particles bounce into one another. The horizontal axis is time. These high points in the waveform are called compressions, and they are where the particles are compressed and bouncing around a lot and thus have a higher pressure. The low points in the waveform are called rarefactions, and they are where the air particles are more spread out and not bouncing around as much, and thus have a lower pressure. Both the graph and particle animation help to visualize sound, which as we know is invisible to our eyes. The measurements are taken at a single point in space. In this case, the pressure was measured by a microphone. In order for your speakers to duplicate this sound, the diaphragm in your speakers just have to move in a similar fashion. The entire sound takes 1/10 of a second for your speakers to duplicate. This visualization is just the first section of the overall pattern of cycling compressions and rarefactions produced from a popping balloon. In just this quick sound, there are about 50 of these cycles. If we slow down this sound to 4 seconds, you can hear some of the cycles between compression and rarefaction. Most sounds last much longer than this quick duration, so in visualizations of sounds, we usually see the squished version of this graph, which looks like this. Let's consider another sound. Here is a running faucet. The moving water molecules apply a force to the nearby air particles, thereby causing the air particles to bounce into one another, thus creating a sound wave. The sound wave propagates throughout the room and hits your eardrum or a microphone, and the waveform looks like this. The difference between the balloon popping and the running faucet is the way the air particles are moved, which can be seen in the shape of the waveform. Another difference is that the sound of running water is continuous, whereas the balloon popping only lasted 1/10 of a second. Now let's consider a significantly more complex sound. This sound of Beethoven's Ninth is constructed from dozens of instruments. Each instrument, when played, applies a force to the air particles around it, thus causing the air particles to bounce into one another, thereby generating a sound wave. So when the waveforms of different instruments meet in the air, they combine to make a new, unique waveform or sound. Wait, let's actually rewind and clarify 3 quick things. First, this animation properly shows how a sound wave is a sequence of alternating compressions and rarefactions. However, it doesn't show how sound propagates in all directions. It propagates kinda like this, as an expanding sphere, so just keep that in mind. Also, second, with this animation, it looks like the particles are traveling. However, in reality, it is the force of the air particles that is traveling. And this propagation of force, along with the alternating compressions and rarefactions, is what constitutes a sound wave. Take a look at the video How Sound Travels to better conceptualize this bouncing-like movement of air particles. And finally, third, this sound waveform is just a quick snapshot of what the entire sound wave looks like. It's about 4/1000ths of a second in duration. To say it differently, there would be 440 of these waveforms hitting your ear in 1 second, or to say it technically, the frequency of this violin sound is 440 Hz. Or to say it musically, it is a musical note A. Okay, so now that we have those details clarified, let's jump back to where we were. So when the waveforms of different instruments meet in the air, they combine to make a new, unique waveform or sound. With simple combinations of instruments, our brain is able to analyze this combined waveform and pick out individual instruments. However, when many instruments are combined, only a trained ear would be able to determine all the instruments used to create the music, because the combined new waveform is so dissimilar to the individual instruments. Furthermore, for us to record and play back the sound of Beethoven's Ninth Symphony, we would just need to convert the pressure waveform in the concert hall into something like the movement of a needle. This is the core concept behind vinyl records. A device measures the force or pressure levels from the air particles in a concert hall or recording studio and graphs them into the grooves on a vinyl record. You can see how the shape of the grooves closely resembles the waveforms we have been talking about. To play this record, a needle just needs to follow the recorded grooves and convert this motion into the motion of a diaphragm, which applies a force to the air particles, thereby reproducing the original sound. Thanks for joining us and learning about sound. If you have any further questions, post them in the
Okay, so here we finished basically the first section of our videos. I think you already have a basic concept of or are familiarized with the sound waves and vinyl and analog signals and maybe also electromagnetic induction and all those concepts. So here I will go through the sound waves. Okay. So first, sound is a mechanical wave. So what is a mechanical wave? In physics, sound is a vibration that propagates as an acoustic wave through a transmission media, such as a gas, liquid, or solid. So mechanical wave means it needs a transmission media to propagate, okay? Either be a gas or liquid or solid or the air. So when I'm talking now, you can hear me because there is air. If we are in this vacuum or outer space, you won't hear any sound because there is no medium. This is what we call mechanical waves. So in physics, a mechanical wave is a wave that is an oscillation of matter and therefore transfers energy through a material medium. Okay, so there has to be this is an oscillation of matter, so there has to be something or some substance that can be vibrated. Mechanical waves can be produced only in media which possess elasticity and inertia. So what is elasticity and what is inertia? So elasticity is the ability of a body to resist a distorting influence and to return to its original size and shape when that influence or force is removed. So actually these two features or properties are pretty important actually. So inertia is the tendency of objects in motion to stay in motion and objects at rest to stay at rest. So if you learned high school physics, this is Newton's the first law, right? The first law. Unless a force causes speed or direction to change. So for elasticity, so there's a body to resist distortion. Okay, so we'll utilize this property later on when we try to describe sound waves from a physical understanding or physical formulas. So when we form the wave equations, we basically use this elasticity and also inertia. I think inertia is the basic, basic laws of motion. Yeah, so unless a force is applied on this object, it won't move. So yeah, simply speaking, it means this. So this is sound as mechanical waves. Okay, it requires a transmission media to propagate, and it follows or it obtains these two features or properties. So physics of sound sometimes propagate through a medium such as air, water, and solids as longitudinal waves and also as a transverse wave in solids. So this means the propagation type of the sound is mostly longitudinal waves, okay? But sometimes it also propagates as transverse wave in solids. So in our next slides, we'll talk about what is longitudinal wave and what is transverse wave. Okay. The sound waves are generated by a sound source, such as the vibrating diaphragm of a stereo speaker. So a sound source is the object, right? The object which produces sound. So when you play the instrument, your instrument is the sound source. When you speak, your vocal tract is the sound source. So there is always a sound source. Okay, there's also always something to generate sound. And then when this object vibrates, the sound will propagate, right, through the transmission medium, either air, water, or solids. And yeah, the other person or the other subject there will hear this sound after the propagation. So the sound source creates vibrations in the surrounding medium. Okay, so it creates the vibrations in the surrounding medium means there is, for example, there is a sound source, and the vibration will be in the shape of a spherical. Okay, it will propagate in all the directions. Emitted from the sound source. As the source continues to vibrate the medium, the vibrations propagate away from the source at the speed of sound, thus forming the sound wave. So the speed of sound in the air is 340 meters per second. Okay, so these are basically high school physics, I think. This is an animation of the spherical compression waves or spherical longitudinal waves. We also see this in our previous videos, right? So the sound source is here in the center, and after the sound source, and when the sound source vibrates, it will create this spherical sound wave surround the sound source and will propagate outside, okay, in all directions. And these sound waves actually are longitudinal waves, okay, here. Okay, so continue with the physics of sound. Here is an illustration of the longitudinal wave in the air. Okay, so at a fixed distance from the source, the pressure, velocity, and the displacement of the medium vary in time. Okay. So here you can see in this picture, the x-axis is the position. Okay, this is the position. This is the physical, where the particle is, and this is the amplitude, or this P is pressure. Actually, you can understand this as amplitude, how loud or how quiet the sound is. And this is the longitudinal wave, and here, when the air particles are compressed, it's called compression. Okay, when so as these places, when amplitude drops down, it is called rarefaction. Okay, and at an instant in time, the pressure, velocity, and displacement vary in space. So there are two different measurements of the sound waves. The first is measured at a fixed distance from the source. Okay, it's not shown here actually. So at a fixed, for example, we take this place. For example, let me use this annotate to show it better. So let's take this point or this place, for example. Okay, and we fix this place. We only care about the movement of this place, so we don't care about anything else. And we see it through time, right? So through time, how this particle will move, it will first move down, right, and move up and down and up. So this is the vibrating of one particle. So this is at a fixed distance from the source, okay? So we fix the distance, we only observe one particle. At an instant in time is what's shown in this graph, okay? So this is basically a snapshot. So this is like some point, like for example, t probably equals 0, let's say. Okay, at this fixed time, this is the position of all particles here. Okay, so that's that. Therefore, this x-axis is the x. Okay, so this is like a snapshot in time that records the current position at this time of all these particles. So you can see here that the movement or the physics of sound can be either described by x or t. Okay, so there are two variables. One is the position, one is time, and this will be much relevant to our later description of the sound wave using physical terms and physical equations. Okay, the particles of the medium do not travel with the sound wave. Okay, so which means the particle will always be here. It will vibrate at its current position. It will either vibrate. If it vibrates up and down, this is the transverse wave. If it moves like back and forth or in this horizontal position, it is the longitudinal wave. But whatever the format it takes, the particles of the media do not travel. Okay, so the particle here, so the particle here, it won't move to here. Okay, it will always stay at its current position, and it will vibrate up and down. Okay, up and down is the transverse wave. Or if it's longitudinal wave, for example here, it will move like the very small limited position, like back and forth here. So this is only very, very small, like only in this range. So it won't move from here to another place. Okay, so the particles don't move. Okay. So during propagation, waves can be reflected, refracted, or attenuated by the medium. We will talk about this concept, especially reflection. Okay, later on when we talk about the standing waves produced by the instruments. Okay. So here is another video that illustrates how does sound travel. Okay, so let's watch this.
The first is that sound waves are a bouncing of atoms or particles into one another. Second, waves can travel very far, however the atoms themselves only travel a short distance. Third, waves travel at the speed of sound, and these speeds are material dependent. Fourth, sequential waves in the same medium travel at the same speed, and thus one wave does not catch up with the following wave. And finally, fifth, the coup de grace of concepts. A sound wave isn't really an object like a steel bar, a wooden table, or atoms of air, but rather, a sound wave is a propagation of force or motion. When we hear something, we are in essence hearing the motion that an object makes, or how kind of that object is applying a force to the air particles around it, thereby causing those air particles to bounce around, and that bouncing is picked up by your ears and perceived as sound. Kind of fascinating, no?
It introduces some basic properties of sound waves. We already addressed some of these. Okay, maybe let me. Okay, so the first is sound waves are the propagation of bouncing atoms. Okay, this is animation.
Second, waves can
travel far but only move a short distance. Okay. So the atoms or the particles here only travel in a very short distance, but the propagation is traveling far through those particles.
Travel very far, however the atoms themselves only travel.
Sound waves travel at different speed of sound. Different speed in different transmission medium. So in the let me do this. Okay, in the air, it's 340 meters per second. In water, it's much faster, and in wood, it's faster in steel. So the speed of sound is actually increasing from air to liquid to solid. Okay, so it propagates at different speed of sound, okay, in different medium. And the fourth, sound waves do not catch up to one another. Okay, I think this is really good.
Travel at the same
animation.
speed, and thus one wave does not catch up with the following wave.
Right. So here you can see, because in the same medium, it propagates at the same speed or the velocity. So in the steel, they will always propagate at nearly over like 5 kilometers per second. So the previous sound wave won't be caught up by the later waves because they propagate at the same speed. Okay.
And finally, fifth, the coup de grace of concepts. A sound wave isn't really an object like a steel bar, a wooden table, or atoms of air, but rather, a sound wave is a propagation of force or motion. When we hear something, we are in essence hearing the motion that an object makes.
So sound wave is a propagation of force or motion. It's not an object because these particles don't move. So only the motion or the force moves through those particles and it propagates, So only the motion will be transmitted from the first particle to the next one, and it continues. So it's not a kind of physical, it's not a physical substance, but it's a force of motion that's going through all those, substances, and it's spread out. So this is another illustration of the properties of sound waves. So now let's talk about the longitudinal waves and the transverse waves. Okay. The sound is transmitted through gases, plasma, and liquids as longitudinal waves, also called the compression waves. Longitudinal sound waves are waves of alternating pressure deviations from the equilibrium pressure, causing local regions of compression and rarefaction. Okay, it's already mentioned multiple times in the previous videos, the compression and rarefaction. Through solids, sounds can be transmitted as both longitudinal waves and transverse waves. So transverse waves are waves of alternating shear stress at a right angle to the direction of propagation. So what I mean, so here, okay, you can see the different shapes. This is the transverse plane wave. This is longitudinal plane wave. Okay. So here the longitudinal waves are waves in which the vibration of the medium is parallel to the direction of wave travels. Okay. So here, open this again. You can see the sound wave. The wave is propagating in this way, right? From left to right. This is how the wave propagates, and the particles at each of those positions also they oscillate horizontally, left and right. So this is the parallel, right? So for longitudinal waves, the vibration of particles and the direction of propagation of the wave, actually they are parallel, they are in the same direction. Okay. So the displacement of the medium is in the same direction of the wave propagation. It's the same thing. It's the same thing. Okay. It only means when your wave is traveling from left to right, your particle is also moving in the same direction here. But for transverse waves, are the waves in which the vibration of the medium is perpendicular, okay, or at right angles. So we say, so here for this transverse wave, the wave is propagating left to right, but the air particles is moving actually up and down. Okay, so for any particle here, you can see here, right? The air particles at a single position, they are moving up and down. Okay. So in reality, it's not necessarily up and down. It might be of some angle like this. Okay, might be of like this. So so we sometimes people say perpendicular just for simplification to distinguish transverse and longitudinal waves much better, which only means the direction of wave traveling is different. Okay, or it's not parallel to the direction the particle moves. Okay, so here you can see the waves actually moving up and down, but here the particles are moving left and right. So this is the basic difference between the transverse wave and the longitudinal wave. Yeah, I hope it can give you a better understanding of this. Any questions? Let me know if you have any questions, in terms of those concepts and terminology, etc. Okay. The sound properties. Here's another video illustrating sound properties. Let's see.
This is what a sound wave sounds like. But what does a sound wave look like? Well, the air through which the sound wave is traveling looks something like this. But if you want another visual representation of the sound, we can hook this speaker up to an oscilloscope and it gives us this graph. We say that this shape represents the sound wave because if we focus on a single molecule of air, we see that it moves back and forth just like a sine or cosine graph. The horizontal axis here represents time, and the vertical axis can be thought of as representing the displacement of that air molecule as it oscillates back and forth. The center line here represents the equilibrium position or undisturbed position of that air molecule.
Okay, so here in this graph, it means in reality, the sound wave in air is actually longitudinal wave, right? The particle is actually moving left and right. But in order to visualize this better, we are assuming we are just to graph it or to visualize it. So here the wave actually propagates in the horizontal direction, but we are drawing the movement of particles, in this vertical direction, up and down. But in reality, it is longitudinal wave, and the particles are moving, as the same direction as the waveform. So here is just a way of representation, but it's not a reality. Okay.
If we turn up the volume, we see that the oscillations become larger and the sound becomes louder. The maximum displacement of the air molecule from its undisturbed position is called the amplitude. Be careful, the amplitude is not the length of the entire displacement. It's only the maximum displacement measured from the equilibrium position. Another key idea is the period of a sound wave. The period is defined to be the time it takes for an air molecule to fully move back and forth one time. We call this back and forth motion a cycle. We measure the period in seconds, so the period is the number of seconds it takes for one cycle. We use the letter capital T to represent the period. If we decrease the period, the time it takes for the air molecules to oscillate back and forth decreases, and the note or the pitch of the sound changes. The less time it takes the air molecules to oscillate back and forth, the higher note that we perceive. An idea intimately related to the period is called the frequency. Frequency is defined to be 1 over the period. So since the period is the number of seconds per oscillation, the frequency is the number of oscillations per second. Frequency has units of 1 over seconds, and we call 1 over a second a hertz.
Okay, so this is a very important concept that we will talk about again and again. The period and frequency. Okay, so period is the number of seconds per oscillation. And the frequency is the inverse of period. It's the number of oscillations per second, okay, which is described by hertz. Yeah, I hope you have a kind of understanding of the relationship and the definition of period and frequency here. Okay.
Sounds have frequencies in the hundreds or even thousands of hertz. For instance, this note, which is an A note, is causing air to oscillate back and forth 440 times per second, so the frequency of this A note is 440 hertz. Higher notes have higher frequencies, and lower notes have lower frequencies. Humans can hear frequencies as low as about 20 hertz and as high as about 20,000 hertz. But if a speaker were to oscillate air back and forth more than about 20,000 times per second, it would create sound waves, but we wouldn't be able to hear them. For instance, this speaker is still playing a note, but we can't hear it right now. Dogs could hear this note though. Dogs can hear frequencies up to at least 40,000 hertz. Another key idea in sound waves is the wavelength of the sound wave. The idea of a wavelength is that when this sound is traveling through a region of air, the air molecules will be compressed close together in some regions and spread far apart from each other in other regions. If you find the distance between two compressed regions, that would be the wavelength of that sound wave. Since the wavelength is a distance, we measure it in meters. Be careful, people get wavelength and period mixed up all the time. The period of a sound wave is the time it takes for an air molecule to oscillate back and forth one time. The wavelength of a sound wave is the distance between two compressed regions of air. People get these mixed up because there's an alternate way to create a graph of this sound wave. Consider this: before the wave moves through the air, each air molecule has some undisturbed position from the speaker that we can measure in meters. This number represents the equilibrium undisturbed position of that air molecule. Then, as the sound wave passes by, the air molecules get displaced slightly from that position. So an alternate graph that we could make would be the displacement of the air molecule versus the undisturbed position or equilibrium position of that air molecule. This graph would let us know for a particular moment in time how displaced is that air molecule at that particular position in space. This graph shows us that in some regions the air is displaced a lot from its equilibrium position, and in other regions the air is not displaced much at all from its equilibrium position. For this kind of graph, the distance between peaks represents the wavelength of the sound wave, not the period, because it would be measuring the distance between compressed regions in space. So be careful, for a sound wave, a displacement versus time graph represents what that particular air molecule is doing as a function of time. And on this type of graph, the interval between peaks represents the period of the wave. But a displacement versus position graph represents a snapshot of the displacement of all the air molecules along that wave at a particular instant of time. And on this type of graph, the interval between peaks represents the wavelength.
So here you may be headache, right? Viewing this. So it's basically this is what I already talked about. It's about what the x-axis represents, right? So here, when it represents x, it is the position versus displacement, and these two peaks, encodes the wavelength lambda. But when the x-axis is time, this two peak is the period. Okay, so these are just some basic ideas.
Interval, but
if you don't quite get it now, it doesn't matter. Maybe you already learned this in your high school physics class. So we'll talk about the physics of sound waves, and also talking about something more. I think. So we're going to take a break now, and after that, I'll get into more of the sinusoidal model, and we will talk more about how we describe sound waves using these equations and physics, and from a more scientific perspective, right? We already have familiarized ourselves with the shape, the concept of the waveforms, but now we want to use a more precise tool to describe sound waves. And I think it will be just more helpful for you to understand this concept, right? In this course, you are not required to master those things, okay? Master those equations is not our purpose, but I think important to give you a scientific introduction to this field so that you have a better understanding of how sound waves are produced, how it's represented, how it's described using mathematical tools. Okay. So we'll take a break, 15 minutes. So we'll come back at 3:50. Okay, 3:50. We'll come back and I will continue with our next part. Okay. If you have any questions, you can ask. If not, see you at 3:50.